So today we are going to discuss about uh, exact differential equation. So what is the definition of exact differential equation? So we're going to define first that what type of differential equation it is actually an exact differential equation. So a differential equation of the form, if we write m of x comma y dx plus n of x comma y dy, that is equal to 0. This type of equation is said to be exact if its left hand member, this is the left hand member of this differential equation. So this equation would be called exact if its left hand side member, left hand side part, is the exact differential equation of some another function u, let's say, such that du is equal to m dx plus n dy. If we can write this left hand side, the left hand side part of this equation, m dx plus n dy is equal to 0. If we can write this m dx plus n dy by differential of some another function u, then we can call this equation, this whole equation we construct here, exact. So this is the equation, exact differential equation, we call it here. So what will be the solution of this type of equation? So its solution would be x comma y is equal to c. So this would be the solution of this type of differential equation. So m is a function of x and y, m is a function in x and y, and n also is a function, n is also a function of x and y. So in this case these are related such that m dx plus n dy is equal to 0. So this whole equation would be called exact differential equation if this left hand side member m dx plus n dy, this can be expressed in terms of exact differential terms of some another function u. Then I can call this equation as exact differential equation. So this is the condition for such a differential equation to be exact. So this is the condition. And its solution, what would be its solution? Its solution would be x comma y is equal to c. So there is some necessary and sufficient condition for a differential equation to be exact. So there is a theorem for that. The theorem is such kind of that theorem is kind of like the necessary and sufficient condition for the differential equation. I write the differential equation as DE as an abbreviation form. I hope you understand that. So for the differential equation, that is m dx plus n dy is equal to 0. So here is the differential equation. I write it here. To be exact, I call it to be exact, is the necessary and sufficient condition is del m over del y is equal to del m over del x. So the necessary condition is the partial derivative of m with respect to y and the partial derivative of n, the first order partial derivative, of course I mean, with respect to x, that should be the both must be same. So this is the necessary and sufficient condition for an equation like that, m dx plus n dy is equal to 0 to be exact. So this is the necessary and sufficient condition of this type of equation. Now we are going to prove this theorem so that you guys all can make a better understanding of this theorem. So I would proceed by necessary condition. So I will prove first that condition is necessary. So the equation I have m dx plus n dy is equal to 0 will be exact if I have mentioned earlier that this equation m dx plus n dy is equal to 0, this whole bunch of differential equation would be exact differential equation, would be called as exact differential equation if if the left hand side part of this equation can be expressed as the total differential of some another function u, which is also a function in x and y. So the equation m dx plus n dy is equal to 0 will be exact if, obviously, if we can express the left hand side as total differential of some another function u. So du is equal to m dx plus n dy, where u is some another function I call f of x and y. U is some function of x and y. But by the idea of total differential, we can write that del u is equal to, if u is a function of x and y, f function of x and y, so I can write it as del u over del x into dx plus del u over del y into dy. So this is from the idea of total differential. So I call it equation 2, and I call it this equation as 1. So this is du and this is du. So equating, if we're going to equate this whole two equation, equating equation 1 and 2, we get, if we compare the coefficient of dx, the coefficient of total differential of x in this two equation, I get m is equal to del u by del x, and if we're going to compare the total differential coefficient of y, that is n, in this equation number 1, I have to number equation number 1 is this. Sorry for the mistake. So n is, if we're going to compare 1 and 2, so the total differential coefficient of y in this equation is n, and here is del u by del y. So I can write m is equal to del u over del x and n is equal to del u over del y. I can write that obviously. Then I have to prove the condition. I have to show the condition is necessary. If we compute del m over del y, that would be del squared u over del y del x and del n over del x. What would be that? That would be del squared u over del x del y. But I have to assume, this is our assumption, that del square u over del y del x is equal to del square u over del x del y. This is our assumption. This is not a thorough based proof, because this relation can hold, either can hold or not, because if this relation holds, that fxy, in this case fxy, and in this case fyx, that fxy is equal to fyx, this relation holds if and only if this fxy, that is partial derivative of y first, and then we're gonna partially differentiate that function, that expression del f by del y with respect to x. So these relation holds if two function fxy and fyx, these both functions are continuous in certain domain. So then I can call that this relation holds in that domain, particular domain. So this is the condition, but I have to, in this case I have to assume, this is our assumption, that fxy is equal to fyx. So we are assuming that these functions are continuous and there is no such complexities in these functions. So we can proceed with further. Is necessary means I have this assumption, this hypothesis, or hypothesis, not hypothesis, this is an assumption. I have given this, that I have given the statement that mdx plus ndy is equal to 0. This equation, this differential equation is exact, and I have to prove del m over del y is equal to del n over del x. This is the necessary condition. This is called the condition is necessary proof. In this particular case, I have to prove that if this equation is exact, then this relation holds. And for the sufficient case, this is actually the vice versa meaning. That is, if this relation holds, then I have to prove that this equation, differential equation, is exact. So we have shown that del m over del y is equal to del n over del x. So we have proved. So necessary condition, I can write necessary condition proved. So this is the necessary condition for exact differential. Next, I have to prove the condition is sufficient, that if this relation holds, then I have to prove this equation is exact. That is, I have to express the left hand side in terms of u, such functions u, some another function u, which is also a function of x and y. So I have to show in that part. So we'll see in the next part, in the next video. So hope you have understand all these concepts. The first part of this theorem, and we will again prove the next part, that is the sufficient condition part, in next video. So thank you so much. Hope you enjoyed.